Okay.
Okay. All right. So, for those of you out in the studio audience, we're doing 2014 question number 5 on molecular structure, which I'll admit I'm biased. I hated organic chemistry, so, because there's just no math. There's just like, oh, we think this is what it does. Okay, whatever.
Look, it's like a flower.
Kind of, yes. Okay. So, but here's what you will see, I promise, on that AP exam, is that they're gonna give you questions like this. Oh, here's a hypothesis. Are they right or they're wrong? What justification is there to support it? And you have to be able to articulate that argument. Okay. So I promise you, you're going to see questions like this. Lab settings. This is what the student thinks. Is he an idiot? Is he a genius? Is he somewhere in between? Okay. And don't write he's a schmuck on the test. It may be true, but don't write that. Okay. So first off, let's just talk broad idea. Or is every compound listed up there, CF4, NF3, OF2, whatever? Are those molecular compounds or ionic compounds?
Molecular.
Why, Wheels? You're right.
There's not metals.
There's not metals. He said you're like Forrest Gump. There's no metals, Lieutenant Dan. I love you, metals. Okay. Sorry, it's late. I've been here too long. Anyway, run, metals, run. So you've got a whole bunch of non-metals, right? Okay. So basically, the short version is that because they're sharing these electrons, it's a communal California thing. Okay, everybody's going to get a ribbon because you get participation points, because basically you don't have a winner in terms of what we call electronegativity and electron affinity, which we'll get into tomorrow in class, except for the juniors who are going to be at the zoo. Anyway, so basically these nuclei don't have enough to completely pull electrons, and even when you have ionic compounds, it's rare that you have like a pure ionic compound. Yeah, we draw structures where these electrons are like locked in place, and we form these and we make the little stick models. The electrons are still moving. It isn't like, oh, they're just going to be locked in here. They're going to share them. They're not going to form an ion. Now, what you might form, and this is one of the questions down below, is a situation where you have a dipole moment, which we briefly talked about on Friday. That when you have a dipole moment, basically what that means is that you have a region of the molecule that has a large, typically a dome of negativity, okay? And a dipole moment is typically drawn with an arrow where the arrow points to the negative end of the molecule. So what happens then is that if you have one end that's negatively charged with a dipole moment, that it can bond with other molecules that also have dipole moments. But if nothing has a dipole moment, then it can't bond with anything else, and the only thing left with is what's called London dispersion forces. Whole nother lecture. Okay, so if you look at the pattern, so let's start with CF4. If you were to actually be asked to be named CF4, what would it be? Quick review from Chem 1. Yeah, CF4. How would you actually name CF4? Huh? Beautiful. Carbon tetrafluoride. 10 out of 10 for fuzzy. Okay? And then you have NF3, which would be nitrogen trifluoride. And then you have OF2, kind of a Norwegian thing. Oxygen difluoride. Okay? Now, so let's look at the pattern. So why do you think carbon tetrachloride is CF4?
It has 4 valence electrons.
It has 4 valence electrons. And then here you have a fluorine, and another fluorine, another fluorine. Now, quick review from Friday. What type of hybridization will carbon undergo? SP, SP2, or SP3? Beautiful answer, Wheels. Okay? Why?
There are 4 bonds. I got really confused watching it, but I got that number is less than the number of bonds. I'm really confused. I didn't understand the video.
Kind of. Okay. There are 4 regions of high electron density. Okay? Right? So here's the deal. Each one of these requires a single electron to form a bond. Here's the problem. If it's a normal carbon atom, you have 2s2, 2p2, right? So these 2 electrons are locked up in an s orbital. They're not free to bond with the chlorines. So by making an sp3 hybridization, the s always gets jacked with. But we're also going to screw up all 3 of the p orbitals. So what happens is that here's a carbon, here's an sp, here's an sp, and then you got another one back like that. Okay. Oh, whole thing. There you go. So when you look at this, you know it's going to be sp3 hybridization because you got, this is as simple as it gets. You got 4 regions of high electron density around them. Each one of these has a single electron that's forming a bond with the fluorine. Now, what would be the structure of this molecule? Begins with letter T. Not trigonal. Tetrahedral. Okay? If you look on the lecture notes that I gave you, for those of you that are taking the test, huh?
I never got those notes.
Oh, here. Dink. Dink. Oh no, wait. There is so much more. There's that. There's that. Oh, wait. There's more. There's that. Oh, wait.
Oh my God.
Yep, there's more.
I forgot to ask.
And yet, wait.
Oh my God.
There's more. Now we're done. Okay. Sorry for that brief interruption to hand out.
It's Christmas.
It is. Or I killed a tree. Okay. So, this is kind of a memorization thing. This is what I hated about organic too. So, on these notes, there's just kind of some basic shapes that you need to know. Tetrahedral, trigonal, planar, T-shaped, okay, linear. They're not difficult. You just kind of have to know them. So if there's anything that you have, wow, I've got to spare 5 minutes, an encore, whatever. Make some flashcards with the names of those molecular shapes, okay, so that you flip it over. Oh, here's an example of it. Oh, here this is. Okay. What do you think this is going to have a dipole moment? Mr. Flett?
No.
Why not?
Because it is balanced in its shape because it has fluorine on all 4 sides.
Yeah, there's no non-symmetry to it, okay? Technically, is there a dipole moment on each one of those because all of these have these big domes of negativity out there with the fluorine? Yeah, but they're all going to cancel out. So they actually will have dipole moments, but you won't have like a net dipole moment. So it's like a tug of war. So you have a 4-way tug of war. Everybody's the same, so there's no net dipole moment. Okay, so why is NF3 NF3? Bless you.
Thank you.
How many valence electrons does nitrogen have?
It has
5.
5.
And it has room.
But it only bonds with how many fluorines?
3.
So that means there's going to be how many pairs of unbound electrons?
1.
1 pair, right? So with that NF3, and again, this is just pure logic. Here you have nitrogen, which has 5 valence electrons. Okay? So you got a fluorine here, a fluorine here, a fluorine here. So this would be, okay, and this is what we build on Friday, okay? Now, what's going to happen up here is that you have this pair of electrons that are unbound. So again, what type of hybridization is this? It's still sp3 hybridization, but this is holding a pair of unbound electrons up here. So what's going to happen is that this dome of negativity is going to push these down. Will this have a dipole moment?
Yes.
Yes, this will have a dipole moment. So if you swap these out for hydrogens, you have ammonia. If they're fluorines here, you have NF3, but it's the exact same idea. Okay? You could put chlorines here, it would be the exact same idea. Something that will accept those 1 electrons. OF2, guess what? Oh, is it going to have a dipole moment? Yeah. How many unbound pairs of electrons? 2, because you have oxygen, which is, so here's your fluorine, there's an electron, so it's going to have a couple of those up there. So that's going to have a very, very strong dipole moment because of the fact that it has 2 pairs of electrons up there, which is going to make this thing even kind of more unbalanced. Okay, so why isn't there anything bonded with neon?
It's a noble gas.
Neon.
Nobody likes neon. Neon's a snob, okay? If you go to a party, neon's like, screw you, I'm not talking to you, okay? It's not.
Neon lids.
Yeah.
Is that Lista's new nickname, Neon?
Neon.
Okay. Then the same thing with argon. Now, look at the structure. And here's part of the beauty of chemistry. Even if you didn't know the periodic table, why is CF4 and SiF4? Okay? They're the same. So how many valence electrons do you think silicon has? 4. Okay? So it's going to be in the same column as carbon does. Okay? There you go. Fancy. Okay? So, based upon the student's hypothesis, what should be the formula of the compound that forms between chlorine and fluorine?
CF.
What'd you get?
I put CF4.
CF4?
Or just one. Or just one chlorine.
Just one chlorine. It's just going to be FCl.
Oh, I put carbon. I don't know what I'm doing.
That's why I was confused.
Sorry. Yeah, CLF. There we go. Yeah, I'm getting there.
I have no doubt.
I'm on the road to getting a 5.
Oh, yeah. Oh, yeah. Okay. So, in an attempt to verify the hypothesis, okay, the fluoride covered other halogens, find the formula ClF3, box below, draw complete. Now, when they say draw a complete Lewis structure, that means every electron has to be accounted for. Okay? Just don't put the symbols. If they say draw a complete Lewis structure, every single electron has to be accounted for. Every one around the fluorine, every one around the chlorine. Don't just randomly put those on there, okay? Make sure the count is right. And again, view this from the perspective of the grader. If all they see is just like random dots, no, bad, don't, okay? Make those dots discernible so they can look and go, oh, okay, here's these dots. All right. So there's any number of ways you could do this, actually. So here's the deal. So you have Cl. Chlorine has how many valence electrons? 7. How many of those valence electrons are going to be bound up making bonds with the fluorine? No.
1.
No. Of the 7 valence electrons around the chlorine, the central atom, how many of those are going to be bound up making a bond with the fluorine? 3. Okay? Because each chlorine, right, is going to give up, or excuse me, the chlorine is going to give up 1 electron to each of the fluorines. Okay? So that's going to leave how many electrons left over? 4. So how many unbound pairs of electrons are you going to have? 2. Okay? Now, this is a subtle thing, but it's important. They don't ask you about this, but I want to point this out. So, when you look at this next question, it talks about a T-shape. Okay, literally, a T-shape. Boom. T-shape. Looks like this. Okay? Chlorine surrounded by this. Okay? And you got 3 chlorines. That's not enough. Okay? So, that's actually up there. That was carbon tetrafluoride. So, here's what you've got. Let me kind of get rid of all of the mishmash here. So, here's a T-shape. Now, let's just play the what-if game. What if it didn't have these unbound pairs of electrons? Okay, if it didn't have them. What do you think the angle would be kind of going across there?
It wouldn't be 90 degrees.
Well, do you think it kind of might flex up a little bit?
Yeah.
Yeah.
Why?
To be further away from the bottom one.
Yeah, okay. These don't want to be near each other, so they're going to kind of flex this up a little bit, right? Now, what if you just had maybe one unbound pair of electrons up there?
It'd be 90.
Well, or maybe like 180 across here, right? But since you have two unbound pairs of electrons, this angle going across is going to be a little bit less than like 180. Okay, like if you split this off, this might be like, 88, and that might be 88, something like that, because it's going to tend to push those down. A structure like this, will this have a dipole moment?
Yes.
Yes. Okay? You do have these domes of negativity around here, but you have an unbound, you have these two pairs of electrons up here, which is going to tend to push those down. This is going to have a dipole moment. Now, so if you have trigonal planar, what do you think the key word there is to understanding the structure of this thing? Well, the tri, but beyond that, planar. Because if it's a planar, that means everything is in the same plane. Okay? There isn't any three-dimensional shape to this. This would actually be a flat molecule. Okay? So do you think this would have a dipole moment? Well, it's all symmetrical. Okay? So when you look at that thing, when it says you have two possible shapes, student does some research and learns that the molecule has a dipole moment. Which of the two shapes is consistent with that structure? Well, the only one that's consistent with the dipole moment is the T-shape. Because the other one is symmetrical and it wouldn't have one. Now, here's the other thing, and we'll talk more about this tomorrow. You guys kind of get the heads up. If you were to compare a T-shaped molecule, let me ask you this. If you were to compare a T-shaped molecule with a trigonal planar, this one having a dipole moment, that one not having a dipole moment, which one do you think would have the higher boiling point? The T-shaped or the trigonal planar?
T-shaped.
Why?
Since it wants to bond with more things, it'd be harder to break those bonds. You'd have to dump more energy in it.
Exactly. So one of the great things to look at as in terms of an indirect measure of the force that hold molecules together is the boiling point. The higher the boiling point, the stronger the bond between those particles. So if you look at nitrogen gas, okay, liquid nitrogen, right? To make liquid nitrogen, it's got to be pretty cold. So when you look at liquid nitrogen, there's a bond. Obviously, that's what allows us to make it into a liquid, but it's not much of a bond, okay? And so it's pretty easy to go above that boiling point because nitrogen isn't very sticky. And some kids like this term sticky, other ones it just kind of grosses them out. But basically, stickiness is a measure of the bond strength between the molecules. And so if they're sticky, it boils at a higher temperature. And then you get into what causes stickiness. Dipole moments are a key thing in terms of stickiness. So it's like making your fingers stick together. It's like, ew, icky, bad. Yeah, not into that. Okay. So we got that one. So you would say in that, justify your answer in terms of bond polarity and molecular structure. You would say with a T-shape, you would have the two unbound pairs of electrons at the top. And that is going to create a dipole moment because the molecule isn't symmetrical. Okay, you would have to say something like that. Just lay that out. Okay. Attempt to resolve the existence of K with the hypothesis stated above. The student reaches the compounds that form halogens and fluorines and assembles the following list. Okay. So let's look at the big picture. You're going from fluorine, chlorine, bromine to iodine. So where are those on the periodic table? Right beside the noble gases. Is that the same list as it appears on the periodic table? In the same sequence?
Mm-hmm.
Yeah. So what's happening to the size of the atoms as you go down? But what do they all have in common?
They all have one balance that's not sure to be
Oh, they all have 7 or 1 short of having the full outer shell, right? Okay. So they have 7. They kind of want 8 because they're all noble gas wannabes. Okay? They want to look like noble gases even though they're really not. Now, so you would think, just based upon, and this is where organic gets weird, you would think that they would all just form like a single bond because they only need 1 electron. But what happens is this when you can get into hybridized orbitals, and these get really, really, really weird in terms of how these orbitals, because you can have like spd3 hybridization. Hybridization gets, the sp, sp2, and sp3, that's like chapter 1 out of like a 10-chapter book, okay? And it gets real weird because then you start messing with d orbitals, and it's ugly. So thankfully the AP basically says we're going to stop at sp3 because it just gets so weird and theoretical anyway. Okay, so if you notice, as you go down the list, what happens to the number of fluorines that they bond with? It increases. But it only, once you get past F2, and then if you look at the bromine and the iodine, okay, what do you notice about the numbers that they bond with? Even numbers or only bond with odd numbers. So what do you think is going to happen with that chlorine bonding with fluorine? What do you think you could possibly get? FCl and Cl F3. So it's just basically a matter of following the pattern. Fill in the blank, kind of. Now, so based upon the concept of harmonic structure and periodicity, which is a fancy word for saying, wow, look at the periodic table, propose modifications to this previous hypothesis to account for, origins of fluorine. Okay, so first off, just make the simple observation. What do you know about the odd numbers? You just have to modify the hypothesis. So when you look at the hypothesis, in reality, what will they only bond with? With a blank number of fluorines. Odd number. So you're going to have to modify the hypothesis and say it will only bond with an odd number of fluorines. Okay? Now, you need to address the fact that there's more electrons. So as there's more and more electrons available, okay, what happens to the number of fluorine atoms it can bond with? It increases. So that's all you'd have to say. Don't make it difficult. But again, here's the deal. So many times kids miss points because they don't state the obvious. Okay? When you're a grader, you have a list of things. You just give kids points. You don't take points away. So you have a checklist of saying, okay, here are some things I need that I'm looking for. Okay? And if you have those things, you get those points. And so one of the simplest points on here was to look at that observation and go, wow, okay, cool. They bond with odd numbers. And that was worth 1 point, was to make that statement. So don't miss an easy point because, well, it's obvious. Well, sometimes science is obvious. Sometimes it's not. Okay. So stop that and now try the... Okay. So let's talk big picture. So, never mind the bear. We'll get to the bear later. So, this goes back to this whole idea of forward reactions versus reverse reactions. Is it favored? Is it not favored? The same old drill. So here's the drill. You have calcium hydroxide, right? It's a strong base, but it's actually not all that soluble in water. So when this is going to ionize, how is it going to ionize?
Into calcium.
Into calcium?
Oh, calcium 2+.
Oh, and I'm going to leave it like that, and I'll show you why it's wrong. And then what else?
Hydroxide ion.
Now, I'm going to write that, and it's going to be so wrong on so many levels. Okay? First off, if you just write Ca, what does that indicate? It's elemental calcium.
That's no bueno.
No bueno. Because elemental calcium reacts with water in a very exothermic reaction to form calcium hydroxide. So, guess what?
Well, you're using up energy by destroying one of the hydroxide ions. That's how you make the...
Get over it. You make it sound like it's a Death Star. It's destroying calcium ions. Everybody run. Okay.
Fission
So,
into pure energy.
now are we good?
No.
No.
Still bad.
OH.
So I gotta have
Oh.
H.
2 hydroxides. Now, let's look at our old friend, the KSP of 1.3 times 10 to the negative 6th. You have a small k value. Is it favored in the forward direction? No. If it was favored, guess what? Calcium hydroxide would be soluble. Okay? Now, 1.3 times 10 to the negative 6, this actually makes calcium hydroxide what we call moderately soluble. Okay? Because it's a small KSP value, but it's a rather large, small KSP value, if that makes sense. Because some KSP values, like 10 to the negative 26th, I mean, like orders of magnitude, much, much, much smaller. So, we can get some calcium hydroxide ions in there, but just, you know, not a whole lot. Okay, so when you get to the first part, here's your answer. That's all you have to do, okay? Don't make it difficult. That's it. Boom.
Would you draw it with the double arrows?
You don't have to. Technically, you should, because it can go both ways because you'll establish an equilibrium.
Okay.
Now, on the second one, they want calculate the molar solubility of calcium hydroxide in 0.1 molar calcium nitrate. Oh, this sounds like it. Okay. But you go back to the same idea of saying, okay, let's roll with this, right? Plus 2 hydroxides. So, when you look at this, is calcium nitrate soluble?
I'm going to say yes.
Very much so. Why?
It's a nitrate.
All nitrates are soluble.
It ain't
Okay? All nitrates are soluble. Now, this is where you have to get a little bit cautious on, because the calcium nitrate is going to ionize into calcium ions and 2 nitrate ions. Now, they tell you that it's 0.1 molar calcium nitrate, so what's going to be the concentration of my calcium ions? Also 0.1, okay? The concentration of my nitrate ions, you don't need that, but that's technically 0.2. But here's why I point this out. Because if this had been something like calcium phosphate, let's say, where that was a Ca2, that means this calcium would be 0.2, and that's what you'd have to put in here. So I'm just telling you, in case it really jerks, and they give you a problem like this in your subscripts, on the calcium or whatever that ion is that you need, isn't a 1, you have to pay attention when this thing dissolves so that you don't get that number. Okay, they weren't in this case, they were nice and said, okay, so this is 0.10. Now again, here's the idea. So here's this beaker, we're going to have some calcium hydroxide down here. Nature wants to be in equilibrium. So if this is 0.1, I got to figure out what this is going to be so that when I multiply everything together, I get that KSP value, whatever it is, 1.3 times 10 to the negative 6. Now, let's talk big picture. What do I need to calculate that KSP value? Concentration of my calcium ions, right? Times the concentration of my, Y squared.
Because you need to.
Right, coefficient 2, right? Now, do I have the concentration of my hydroxide ions?
Nope.
No.
That's bad.
It's bad. So we're going to let this be 0. Okay? So what's going to happen here is that this is technically going to start as 0.1. You technically usually don't have to put this in. But here's the whole idea. So some of this is going to ionize. So I'm going to add some X here, right? And then I'm going to add some 2X over here. So why did I put 2X there?
There's 2 of your X in that.
Yes. Now, if I add 0.1 to X, this X isn't going to be significant, okay? So my calcium ion concentration is just going to remain as 0.1. Technically, it's plus X. If you really want to be a big dog on the test, write plus X and then not significant if you really want to be a big dog. But when I take 0 plus 2X, that is significant, so that becomes 2X. Okay. So once I get this 2x, then what am I going to do with it?
You're gonna punch it in.
I'm going to punch it in. Yeehaw, doggies. So there's my KSP value, which is going to be my calcium ion concentration, which is 0.1. Now, am I going to put x or 2x in here?
Ooh, you're gonna put 2x.
I'm going to put 2x in there.
4x squared.
But then I have to square it. Oh. So what do you get?
Numbers.
Numbers. Hopefully you get
Wait, spoiler alert.
0.00, I can't even remember my handwriting, 0.0018?
Yeah.
18. Okay? So there's your missing value. So now when I plug that back in, and here's how you can see if you got this right. Take that 0.0018, plug that in here, multiply that by 0.1, see if you get 1.3 times 10 to the negative 6. If you did, hey, groovy. Now, here's the deal. What would happen, here's a quick refresher course. So up here, I've got some calcium ions floating around, I've got some hydroxide ions floating around. Okay? Notice that my hydroxide ion concentration is a lot less than my calcium ion concentration is because of the fact, now, here's what you can't do, look at this and go, oh, that's 0.1, that should be 0.2. Okay? If it was a straight ionization, that would be true, but it's not. It's a KSP calculation. So that's why this is 0.0018. Let's say that I dump in some hydrochloric acid. What's going to happen to that precipitate? Fuzzy? Why?
Because your H plus is going to find bond with the OH minus.
To make?
Water.
And so what's going to happen to the concentration of my hydroxide ions?
Gonna decrease.
It's going to decrease, so nature flips out and goes, oh my God, I'm losing hydroxide. What's the only source of more hydroxide ions?
The water.
No,
No, like the substance in the bottom.
calcium hydroxide, otherwise known as the precipitate.
The substance in the bottom gets you a spot on your.
So
Yeah.
that's going to go like that. Okay, so let's say that we add a little bit of nitric acid. We notice that, or hydrochloric doesn't make any difference, okay? And some of it's going to dissolve, and nice could. Okay, no worries there, all right? But let's say then I double, let's say I'm just going to add some straight water to it. Okay, I'm going to double the volume of the water. But there's still some precipitate that's down below.
Still saturated.
Still saturated, so what's the concentration going to be?
They're the same.
It's going to stay the same. Now, what if I added a bunch of calcium ions into the solution? Then I would make more precipitate. Okay. All right. So then represent water molecules as the bears, the water molecules, the Mickey Mouses, whatever. Okay? But let's talk about this. These are going to be what? Hydrogens or oxygens?
The small ones are the hydrogens.
Yeah, here's my hydrogens, right? So this end represents your oxygen sitting in there. So is this end your positive or negative end?
Positive.
So is this going to have a dipole moment?
Yes.
Pointing which way? Up or down? Down. Okay? So now we have goatee bear. Okay? Why don't you throw in the dipole moment? What did she just say? Don't lie.
I didn't say anything.
I think you did. Okay.
What did you say?
All right.
You killed Liz.
That's okay. So here's the calcium ion. So which end of the water molecule is going to point towards the calcium ion?
The negative side.
Yeah, so you just need to go something like this. Okay. Dink, dink. And if you have some time and you want to go in and put little smiley faces on, you know,
Maybe that'll get you more points.
no, it won't. Okay.
Right in there, Dave.
You can write a
Does
little
it-
note that says, "Dear grader, just thought I'd brighten up your day." Smiley face.
It's a little too negative down here.
Yeah. Hashtag polar bear, so to speak. So,
Polar.
yeah, got
Oh,
it? Yeah.
what a slammer. What a knee slapper right there.
Okay.
Lots of
I actually just made that one up. I wasn't.
I like that one.
I did too. Okay, I'll have to work that into the shtick
I
somehow.
should put that as a title.
Okay, so now, there are some multiple choice questions. So, stop that. Okay, so let's start with 39. Okay, and I purposely went through and picked some stuff that you're going to have to think through and maybe piece some stuff together. So, when you look at 39, so here's the whole key to 39. Is that, do you think both of these materials are going to be at the same temperature? When you've got the two cotton balls.
Yeah.
Yeah. Okay? They're both going to be at the same temperature. Temperature, remember, is a reflection of kinetic energy. Okay? So when we measure temperature, we're actually talking about the kinetic energy of the particles. Well, kinetic energy is, and this equation is on your sheet, and there used to be a lot more of them. They simplified this a lot over the years. But the kinetic energy of a molecule is 1/2 mv squared, right? So think about this. So you're going to put these two cotton balls in the end. It's going to be a volatile liquid. Okay, it's going to go from a liquid. It's going to have relatively low vapor pressure. It's not going to have a very strong bond that holds molecules together. Okay, that's why it's going to turn into a vapor. So in this tube, these two vapors are going to start drifting towards each other. Okay, they're going to meet in the middle. So what do you think is true of the speed of each particle? They're gases. Are they going to be moving at the same speed if they're going to meet in the middle?
Yeah.
Yeah, because
In the middle.
if Fuzzy starts running at that end of the hall and I start running at that end of the hall and we run into each other in the middle, we both have to be running at the same speed. So if they're at the same temperature and they run into each other at the same in the middle, they have to have the same kinetic energy, which means they have to have the same velocity. So the only way they have the same velocity is if they have the same mass. So pick the two that have the closest molar mass. So which two have the closest molar mass? Well, look, bromine's huge. So you can eliminate that. So let me give you a hint. The answer is A. Okay.
That was a good hint.
I was like, I don't know what I'm doing, so I'm just gonna keep it there.
Circled A.
It was a good answer. Okay.
Yeah. Can you be there on my AP test?
Yeah.
So let's talk about semiconductors. Semiconductors are usually made of materials that you can alter the structure. Like, for example, your phones work off of basically semiconductors. This is why we call it Silicon Valley. They tend to be the metalloids, which are along that dark stair-step line, kind of on just to the right of the periodic, on the right side of the periodic table. Okay, and so what we found is that we can alter their conductivity, which you can also means you can almost use them as like resistors, because some materials you want to conduct very easily, and other ones you don't. So here's the first thing you have to know about electricity. Electricity is the flow of negatively charged electrons. Okay, it actually creates an electric field. That's a whole nother discussion, but that's the short version. So, so when you look at your choices for B, right away, which one can you eliminate? Excuse me, on number 40.
I'm gonna say B.
Let's go with B. Because you're not going to have mobile positive charges.
That doesn't make sense.
Okay, it doesn't. Now, so the whole key to this is that you want to increase the conductivity. The only way you can increase the conductivity is if you have more electrons that are available to flow through the structure. So you're going to have to look at a periodic table. So if you look on a periodic table, so you have silicon, right? Okay. Now the whole key to this is phosphorus is 1 to the right, and germanium is 1 below. So if you compare silicon and germanium, what do you know about the number of valence electrons?
They're the same.
They're the same. Whereas phosphorus is going to have
One more.
one more. So with that said, what do you think the correct answer is?
Probably A.
Hey.
Probably A.
My favorite word.
A. Yeah, okay. All right. So let's talk 41. So nitrogen molecules absorb ultraviolet light, but not visible light. Iodine, both visible and ultraviolet light. So you have to understand how this deal works. So here's nitrogen, and here's iodine. So if you had a tube, okay, and this is what's known as a dark line spectrum. So what you would do is that you would shine all the different types of light through the sample of nitrogen, all the way from ultraviolet to visible light. Okay, so does UV have a shorter wavelength or a longer wavelength than visible light?
Shorter.
Shorter. It's ultraviolet, right? So that means it has more energy, which is going to be a key component of the story. So basically, we're going to shine all this light, UV all the way through visible light, through a tube of nitrogen. And what they tell you is that nitrogen absorbs UV light. So out of this, everything is going to come through except for UV. So in other words, the reason that we call it dark line spectrum is that you would see all the forms of light make it through, but you would have a gap at the UV line. Okay? So that means now physically what has to happen within this nitrogen molecule to absorb that UV light? What has to happen?
Doesn't it have to have electrons?
Yeah. So a certain electron within that structure has to gain just that amount of energy to jump from its ground state to a higher state, and then it doesn't like it there, and then it's going to come back down. Okay? So the only way that can happen is if there is within this structure, there is something that can absorb that UV light, it jumps up, comes back down. Everything else passes through, which is kind of a cool thing. What's the air made up of that you breathe, mostly? Guess what? Light pretty much comes through unabated. Okay? It does. Now look what they tell you about iodine. Iodine, if I shine all of that goes through, what else? What happens with iodine that's different?
There's no visible light.
You still get a gap in the UV, but what else do you get?
Visible light.
You get a gap in the visible light. Oh, visible light. Okay? So this one can absorb UV light. This one can absorb UV and visible light. So that means this iodine has the capacity to absorb an electron or a photon that's in the visible light. So is the visible light going to have a bigger or smaller jump than the ultraviolet light does in terms of the electron? For that electron to absorb a photon of visible light that has a longer wavelength and a lower frequency, is that going to be a bigger energy jump or a smaller energy jump than UV?
Smaller.
Smaller, because remember, as wavelength gets bigger, frequency gets smaller. So visible light has a longer wavelength. So this jump here is going to be from some ground level here. There's my UV jump. That's going to be the same for both of them. But to create a jump in the visible, that's going to be a smaller difference in those energy levels. Okay? Now, with that said, what's your answer to number 41?
I'm going to go C.
You're going to go with C. That would be wise.
Yeah.
Okay? That would be wise. Now, iodine has a distinctive color to it. So here's the deal. The reason that nitrogen is clear basically is because nitrogen doesn't absorb and emit anything in the visible spectrum. It lets it all go through, which is nice that nitrogen is that way. If nitrogen had the properties of iodine, what that would mean, if you ever see iodine, cloud of iodine has like this bluish, purplish haze to it. If nitrogen acted like iodine did, our skies would be completely different. because everything would have this hue to it, because it would be emitting and absorbing light in the visible spectrum. It doesn't, so this is why nitrogen and oxygen are cool to have in our atmosphere, because they don't interfere with light and they let that pass through. Okay, now 42, real quickly. What do you think makes something on this hardness scale? Do you think the particles move easily or more difficult?
I'm going to say more difficult.
Yeah. If you have a stick of butter that's come out of the freezer, or if you have a stick of butter at room temperature, what's softer?
Room temperature.
They can move past each other easier, right? Okay? So the whole key of alloys is that you're taking a metal and you're mixing two metals together. And you can alter the metals that you add to it. So when you look at this, you're told that the the gold and copper alloy is harder than the gold and the silver alloy. Well, look at the sizes, right? So when you look at the atomic radius of copper, that's smaller than the atomic radius of silver. So when you put that copper in there, it doesn't displace as much space, basically, in this metallic structure. So since it doesn't displace as much space, those existing gold particles then will stay in place easier, because it's kind of like putting rollers in there. So if you have like a smaller ball bearing, it's harder to get those things to slide past. So with that said, the correct answer is C. Beautiful. Okay, now let me kind of draw what's happening on 45, because this is a weird redox reaction, the way they have these listed. And they made it even more confusing because they give you half cells 1, 2, and 3, and then like galvanic cell X is 1 and 2, Y is 1 and 3, Z is 2 and 3. Literally, the first thing I did when I got this is that I drew a picture like this so I could visualize what was happening, okay? Because you've got numbers and letters and all of this weird stuff, and then your half reactions aren't really half reactions because they're full redox reactions, and you're going, wow, this is just kind of weird. Okay, so let's start with 45. So you're going to end up with 45, which is a combination of 2 and 3. So when you get this, you got the 2 volts for the aluminum and copper, and then 1.22 volts for the aluminum and the iron. So play the numbers game. So this is like Hess's law. 46 is B, 46 is C, 47 is C, and 55 is C, and 56 is D. So if this is like Hess's law, okay? You want to manipulate the equation so that you end up with an answer on 45B. So what do you, 45B, got it. 45, the answer is B because it's 0.78.
Woo!
How do you get there?
Okay, look. If you look at what you want to end up with, you want to end up with, like, start with iron. So if you look at reaction Y, okay, galvanic cell Y, that has iron as a product, okay, well, I know that's going to get flipped so that I end up with iron as a reactant. So as soon as I flip galvanic, or half cell 2, okay, or excuse me, galvanic cell Y, as soon as I flip that, that voltage now becomes negative 1.22. So if I take 2 and add the negative 1.22, I get the 0.78.
That's what I did.
Okay.
Okay.
God, I had that.
That makes more sense.
Ooh.
I thought
Okay.
these were like 3 separate things, like
No.
running at one
Can we
time.
use this on the test?
What?
This
Yeah, you
solution?
can.
No.
No?
No.
No.
They do not give you the standard reduction. They will give you portions of it if you need it. Okay?
Oh, you were wrong. You see my expectations.
So would you kind of use like Hess's law on this?
Yeah, basically it's Hess's law with galvanic cells.
Okay.
That's what I did.
Okay. Now, so this is why I drew a picture. Literally, this is the first thing I did when I got this problem. So you look on 46, okay, it says in galvanic cells Y and Z, which of the following takes place in half cell 3? So you got letters and numbers and half reactions and all this good stuff. So here's the deal. So what I did is I said, okay, here's what's happening in half cell 1 with my aluminum. Here's half cell 3 with my iron. So if you look at what's happening in cell Y, so the cell is referring to this whole thing, okay? The cell is the whole thing, okay? That whole thing is one cell. So if you look at this, so you've got on Y, look what's happening to the iron. You're going from Fe2+ into elemental iron. So what's happening to the Fe2+? Is it being reduced or is it being oxidized?
Reduced.
Reduced, because you're gaining electrons. Okay? Now, then on Z, okay, so if you go down to Z, which is this one, now what's happening to the iron? Now you're going from elemental iron into Fe2+. So in that case, iron is being, so the correct answer for 46 is C.
I don't like those questions.
Well, it does. It reads weird. I'll admit it. Now, on 47. So now we're going to go from a 5 molar concentration, from 1 molar to a 5 molar concentration. So here's what's important. Okay? So on this one, we're going to dump a lot more ions in here. Okay? We're going to go to a 5 molar solution. So the electrons are flowing here, and I'm producing elemental iron. So when I dump a bunch of ions in there, what do you think is going to happen to that voltage? It's going to increase, because there are going to be a lot more iron ions going, hey, yo, come on, let's party. Okay? So this is going to greatly increase my E value. Now over here, if I dump a bunch of ions in there, now what's going to happen? What's going to happen to my E value? It's going to decrease, because now the one way to look at it is that now I've made this very, very, very concentrated, and it's harder for those ions to go into the solution because the hallway is really crowded. Okay? Now, you can also look at it, they don't give you the Nernst equation. You can also look at it as E equals E naught minus 0.0592 over N times the natural log of Q. I think that's it. Don't hold me to that. So, basically, when you overload that product side, okay, over here, it's going to make that E value become smaller. Over here, when you overload the reactant side, it's going to make E go up. So it's odd that they ask you about the Nernst equation, but they've taken the Nernst equation off of the exam sheet. So it's just kind of weird. 55. You're talking about a buffered solution. Is 55A even an option for a buffered solution? No. Categorically no. Why not? Why is A not even a possibility of being a buffered solution? Yeah, it doesn't have the acid and the anion off of it. So A is just completely out of the question. So, here's the deal. If you want a Ka, a pH around 7.5, what are you going to look for? pKa close to that. So which one of those only has a negative log even close to 7.5? C. So the correct answer is C. Now, on the back side, on that last one with all the polar bears. So let's look at this. So you've got a graphical representation. So right away, why could it not be A and B?
Because their molarities are equal.
Yes. When you look at the diagram, do they have equal molarities?
No.
Okay, so right away, A and B, gone. Okay? Can't even be an option. So, C and D, let's talk about that. So, here's the deal. when you look, and you actually, on this situation, I'd go, even though you don't have to, let's look at the whole equation. So you got silver nitrate and magnesium chloride forming what?
Silver chloride and magnesium.
Yeah, you get magnesium nitrate and silver chloride. All chlorides are soluble except for
That one.
silver, lead, and mercury. Okay? So, here's the whole key. Now to balance this, that's CO2. I need a couple over here, I need a 2 there, life's good. So, what do you notice about the magnesium chloride and the magnesium nitrate? They're in a 1-to-1 ratio. But this is where this gets really, really, really tricky. So, since it's in a 1-to-1 ratio, you're tempted to choose C. Okay? And here's the reason why. Because, wow, I got 1 molar magnesium chloride. This is in a 1-to-1 ratio, so I should have a 1 molar concentration of magnesium nitrate. Because it's in a 1-to-1 ratio. Seems logical. It's not logical. Why? Why is the answer D? Look.
Volume increases?
I've doubled the volume. Oh. Oh, tricky. So by doubling the volume, the concentration becomes half. So the correct answer is D. Okay.